All right, so I think we're gonna move forward today. Now it's time to construct. So we've got the code in here, right? Running it that builds this group, and then we have a center. We have an order. We have the quotient, and basically we have also the rule that all non-identity elements satisfy the G3 equals 1, confirming the exponent is 3. I'd like to dig a bit more into this, but it's a distraction right now. Like, as in, like, why there are only two, right? Why there are only two groups of order size 3 and quotient 9, right? Why there are only two? I mean, maybe it's a side question, but like, I guess, no, I shouldn't ask these now. Let's try to push forward. I have a side question for these, which is, let's see, yeah, that's going on. So the side question is how different they are, right? Because essentially it means that then it must be another center, right? Well, let's think about it. The way that this is, and that's I shouldn't be doing this, but yeah, the way that this is done is the operation is defined like a1 plus a2, b1 plus b2. So these things commute. So it's the last element, right? Which does c1 plus c2, and then it does a1 and b2, a1 and b2, a1 and b2, right? So a1 must be 0, and so maybe that happens when one of these elements is non-zero. That then we have, maybe that's, you know, maybe that's why, like that's why we have two. And I don't know why do we even have notations for such specific things. Whatever. Now we're getting into the next step, which is, now we have these and we want to do dr times s. Okay, let's construct dr times s. Cool. So here, now take that code and add a definition for C2 squared for the C2 squared group, and let's build the semi-product of S R times C2 squared as being the one we just built now. Let's do this step by step, okay? As I want to understand, how are we going to define the operation based on an induced action from C3 to C2 square. And we can do that because C3 is a subgroup of these, right? Of S. So go step by step. Adding code and ask me if I follow. Let's see what it does. Okay. S is Heisenberg group. We need an action of C2 on S. No, stop. Stop. The semi-product we're defining is C2 squared. Sorry. Yeah, C2 squared time. It's my mistake. R times S. So we need an action. So we need an action from S. Yeah. From S2. From S on C2 squared. Yes. Since requested an use action from we'll interpret this as defining an action where the cyclic group acts on step by step. So define the group as let's go straight to the code. So define C2 squared. So basically Z2 is Z2. It's asking me, do you follow so far? But then it continues defining step 2. Oh, come on. Generate elements of S. That's what I don't like. Z3. No, okay, that's fine. Automorphisms. Okay. Oh, Klein multiply. Define the action of S on C2 squared. Okay, this is what we need to understand because automorphism is C2 squared. Okay. The semi-dark product. Okay, so the it's the automorphism C2 squared is basically okay. I understand. I think it's what's nice is what I'm understanding now is that the fact that we are looking at C3 for the automorphism is telling you that just this is just a mapping from the because the elements, the generators are the same. This means it's groups of 3 elements, right? I guess that's why it makes the definition easier, maybe. So automorphism C2 squared. A, B, C equals S if B equals 0 and C equals 0. Subgroup of order 3. Then K equals A, or if K modulo 3 is 1, then return these. Otherwise, return that. automorphism. Is that the action? I'll have to trust it. But essentially, let's break it down so high level. So it defines an automorphism C2 squared, an automorphism. Remember that an automorphism is taking, so the action, yeah, exactly. The action had a specific definition, which is basically the elements, I forgot about that definition, but it was like multiplying the elements, but then transforming an element S based on that automorphism. And so that's what it's doing here. It's transforming what is X, by the way? Oh, X is the function. X is return lambda X. Okay. What? It's actually returning a function. Okay. Okay, that function, okay, I get it. Okay, so it's returning this function, like a lambda function. That basically takes in an X, which is a two component element, a two tuple. And if it's different than 0, 0, then it returns this. If it's, yeah, okay, so essentially this automorphism returns two different lambdas. Okay, let's go. That's all good. Define the semi-direct product operation. Semi-direct product operation. It's taking G1, G2, and what is that? Semi-direct multiply. Automorphism C2 squared of S1 that returns that function, and then we apply this function on X2, Y2. And then, yeah, I think that's doing, this is like, I'm trying to remember, I'm trying to pull back. What was the explanation of the group structure? I think it was maybe it will be explained here actually. All elements as pairs, create permutations and verify the properties. Follow? No, I don't follow. Yeah, wait. Semi-direct multiply. That's exactly. So this was the definition of the action. The automorphism is here. The automorphism C2 squared is here. That's what maps an element of. That's what, given an element of S, transforms an element of C2 squared. Exactly. Then we have a semi-direct. The semi-direct multiply. That's the operation of the group. Yes. Generate the elements. So here it does basically it's using C2 squared elements and the elements of S. It's generating all the elements, and then it's creating all the permutations for the semi-direct product. Why is it doing permutations? Yes, okay, because it's taking the elements. Yeah, those are the elements are just the generators, and then it's creating all the permutations. So finally, we're creating G, which is this permutation group. And so, okay, but it's kind of like, yeah, I mean, it makes, I'm trying to understand how it did it, but it just kind of makes sense. So it seems like the way that we're defining the groups is you define what generates them, you kind of define, you define the operation, right? You define the operation of the group. So here you have the Heisenberg multiply, and then you also have we call it multiply because I think that's just what makes it easier, right? Instead of just saying operation, but that would be the Heisenberg operation, or the operation of the group of the Heisenberg group. Then we have the Klein multiply, because that's the operation of the Klein 4 group. That's the C2 squared group. So we use then we're also generating the automorphism, which we're using here. We're using here as part of the multiply of G, right? And that's this formula here, and that's how you calculate the. That's how you are calculating that's how you are building up the operation of the semi-direct product group. And that's what we're doing, xy, and then we do the Heisenberg multiply, and then we return x, y, and s, basically. This seems correct. Then we're generating the elements by doing the Cartesian product. And then we're creating permutations. And to create the permutations, we need to actually do the semi-direct multiply. That's because you are operating them. So we have the permutations. And then at the end you have, yeah, basically that's how you end up with a group. So you have the group G. So now that's what we have that, basically. How else can we verify that is correct? The order should be 108, and the very fine on abelian property. I mean, yeah, sure. Is there anything else we can verify? It seems like the steps seem logic, and I'm happy that I can understand. Oh, whoa. It says order is 324. That is too big, though. Does it have to be 108? If it's 27 times 4. Is it though? Okay, so the code, now let's reason that. That's good. So the code speeds out an order of 324 elements. But you're claiming the order should be 108. Now let's think about these. The order is the elements. I think the code is right. I think 108 is the amount of generators. Is it so that 108 is the amount of generators? The Cartesian product of each group, but order is then the amount of elements permutations of these 108 elements, right? But it seems too. Am I correct? Wrong? Can you help me understand which is right? Which is correct? That still seems like a small number, 324, if it's like 108, because 108 elements, like they permute in like an insane number, unless a lot of these permutations are just equivalent, right? How did it come up with group order? G order, okay. Permutation group of the semi-direct permutations. So what did it do? So the semi-direct elements, and then what it does is for each I and H in semi-direct elements, the semi-direct multiply is the result. Then the permutation dictionary Is this function correct? order 4, and this is order 27. Well, there's the question is what exactly the expected order. The semi-direct product should have order equal to the product of the orders of the two groups. Elements, 27 elements. The elements of the semi-direct product are pairs, where x and y belong to C square and ABC belong to S. The Cartesian product of the element sets gives exactly 108 elements, which should correspond to the group's order, assuming the group operation is correctly defined. Semi-direct product, correct permutations for generators only. Ah, that's it. It was creating, I think that's what was happening. So it's the number, yes, it's the number of pairs. That's so it should be 108. It's an error in the code, yeah. So checking the partition function. Semi-direct elements. So it iterates over each of the 108 pairs, computes the group operation GH, maps I to H, creates a SymPy permutation object. The logical function is correct in principle, it generates permutations based on the group operation, which is a standard way to present a group in SymPy. However, if the output order is likely lies in the group operation, semi-direct multiply, interesting, which produces incorrect results. Duplicate or incorrect permutations being generated. The action being incorrectly defined, affecting the group structure. So diagnosing. The output order is 300, the group generated by the permutation is larger than expected. Let's hypothesize why. Expected order, semi-direct product should have 108 elements, has length 108, and its Cartesian product, yeah. So this makes 1, 0, 0, act as a 3 cycle, which is valid. The action might be too restrictive, or there's a subtle error in the how permutation is generated. However, the most likely issue is the permutation group construction. Okay. Could include additional symmetries if the action or operation introduces unintended relations. Let's run it. Okay, so now it says 108, so it seems like it fixed it. What did it change? Generators, the semi-direct permutations. I think the problem is that it's yes. What? For generators only. Instead of using all the 108 permutations, which risks generating a larger group, we can define the semi-direct product using generators of S and C2 squared adjusted by the action. The Heisenberg group S is generated by these and since by these. We'll construct permutations for these generators. Okay. I think so. I think what was happening is that it was doing it as if it was just a regular product, maybe. I don't understand why it selected these generators. Is it because, so how? Depends on action. Ensures that generators produce all elements via the operation. Really? It's a billion so elements that produce all four elements. Minimal generating set is 1 0. I'm not so sure I understand that. I'm gonna pause this video here. So we are not okay. So let's pause it here. Now so the question is, how do we come up with these small set of generators? Now it's obviously kind of working or giving us the correct result. And this is gonna have, because ideally I wouldn't like this to be hard coded, but basically, can you build the function? Okay, can you build a function that calculates the generators list instead of hard coding it? This should help me understand that. That's one thing. And then the next question to ask is, how can we calculate KB? How do we in SymPy can we embed a group into a field? So I'm gonna ask that in another sorry, in another chat. So how can you embed a group into a field using SymPy? So what I mean is, define a cyclic group, print G. Define a finite field, prime field with 5 elements. Construct the embedding. I'm not so sure if embedding is what I mean. GF. Galois field, yeah, I think so. GF flux. Grok.com. What does, and the next question is, what does having a field K and a group G, I want to calculate KG and I want to know what blocks of KG mean. Can you help me understand the meaning of blocks? Stay brief, short, high level. That's that's the only thing that we're missing. Cool. Here we have the. So here now what it's done is semi-direct multiply, get semi-direct generators. Okay, so it's done these here. Yeah, okay, come on. You've you still have color coded them. That's not what I meant. It should still run the same, but that's not what I meant. That's definitely not what I meant. That's still the identity, S identity, and then C2 generators and S2. That's not what I meant. This is what I need to understand. How did it pull this out? And here it says KG is if K is a field, is a group, then it denotes a group algebra or a group ring. Vector space, blocks of KG in the context of the group of functions, especially when K is a field of characteristic P bigger than 0. Okay, we know that there's a characteristic 2, whatever that means. Often P dividing the order of G. The blocks refer to the indecomposable direct summons of Kg as a ring or module over itself. This arises from the block decomposition of Kg in modular representation theory. The group can be decomposed into the direct sum of two-sided ideals called blocks, which are the building blocks of its structure. Okay, we're getting into something there. Can the number of groups be calculated, of blocks, sorry. Simpai. Okay, we're getting there. I need to understand how these generators are how it came out with these generators, and then move on with these other two topics, which basically means doing the whole thing with a group algebra and try to understand. Okay, it's kind of gotten stuck with this. Anyway, see you in the next video.